she will speak about root to cause in anatomic mechanics. Please, the floor is yours.
Okay, thank you very much for an introduction. My name is Patthamon Kongkhambut from University of Hamburg. I'm working now as a postdoc in a group of, is everything all right? Okay, in a group of Professor Andreas Hemmerich. So let me have my laser pointer here, you can see. Okay, and the title is, as you said, A Route to Chaos in an Atom Cavity System. Let me first introduce about what is a route to chaos. So a route to chaos describes a process in which a simple attracting set of a dynamical system becomes chaotic as an external parameter is varied. This is said. For example, commonly known routes to chaos are period doubling route to chaos, where if you have, for example, first an attracting set of, let's say this is a limit cycle, where you have your system exhibit an oscillation with a single frequency. And in the phase space, this looks like you have a one loop trajectory. Then if it becomes unstable and going on a period doubling bifurcation, then this one single loop become two winding. As the second frequency that arises is one half of the frequency that is there before. For example, what you may know is about the logistic map, where you have this growth of your population X, which is depending on a parameter R. So here R is an X axis, where you see that for some specific case of R, you have a growth rate that is a fixed number. And then your population across one critical R, then you have two number of populations, then 4, then 8, and so on and so on. And this route to chaos give you like from a simple set, and then you have some chaotic behavior later. And recently, it has been explored in a driven dissipative Rydberg gas that this period doubling route to chaos can be experimentally seen there as well. Another less commonly known is Hopf bifurcation. This, if you now start with, again, the limit cycle, then it undergoes a Hopf bifurcation. The signature is that the second frequency that arises is not commensurate to the first frequency. Then you have a quasi-periodic behavior, such that now your attractor looks like a torus. And this process can go on and go on until you reach chaotic phase. The example of this is a Van der Pol oscillator. What you see now is just a phase space that looks like a limit cycle that you see. It is not yet become chaotic, but yes. And the next application is that you can see in a biological system, for example, in a predator-prey interaction. And what we're going to talk about today is that a Hopf bifurcation route to chaos in an atom cavity system. So we will focus on this now. So first, let me introduce about our experimental platform. We have an atom cavity system where we have this Bose-Einstein condensate of a rubidium-87 trapped magnetically in the center of a single mode cavity. Here we have an external parameter, which is the pump, where you can pump the system transversely. And we have a, opportunity to detect the intracavity photons. If there's a photon in the cavity, we can detect it behind one of the mirror because it has a fixed loss rate. Now we will continue. The first step of our experiment is that the self-organized Viridian phase transition, which most of you may have heard about. This happened when, let's say, when we pump the system below a threshold, let's say, called lambda SR. The system is a normal phase where you have no intracavity field builds up, and all the light of all of the photons that scatter from the pump into the cavity are destructive interferes. So you have no light in the cavity. If I take absorption imaging of my atomic population, you would see that you see this kind of a momentum spectra, where you see most of the population is in 0-0 mode, where there's a small fraction in ±2 here, which is showing that the system is in the standing wave potential of the pump. Then if I crank up the pump strength across the threshold lambda SR, what happened is that we see lights in the system, because now here our atomic population self-organized into a checkerboard pattern. And with this pattern, it scattered perfectly. It fulfilled the Bragg condition that the photons can scatter from the pump into the cavity and vice versa. And this also built a long-range interaction in the system as well. Again, if I take an absorption imaging, I would say an additional plus minus 1 H by K mode appearing. And this shows that in the real space, our system self-organized into a checkerboard pattern. If you want to talk about this in a bifurcation language, we would see that now the tuning knob is the pump parameter, is the pump intensity, lambda. And now if we have below critical parameters, then we only have a normal phase. Then across this critical value, we have two possible self-organized state that system can self-organize into, which is the even parity or the odd parity. And these two happen 50-50, we will show later. Then what we can see is that, as I said, we can detect the light that leaks through one of the cavity mirror. If we plot that against time, this is a real experimental data. That's x-axis is time, where we ramp the pump strength linearly. As the pump strength increase across the threshold, let's say here, we start to detect light in the, let's say NP is the number of photons in the detector behind here. And what we can detect is also the phase of this light in the cavity, which is plotted in blue. So below the threshold, there's no light, so the phase is undefined. So it's go crazy. Then once it fixed into one of the pattern, let's say that the light scattered from the pump to the cavity has a fixed phase because our system self-organized into one of these. And by using the knowledge of this phase, we can detect that we can plot a histogram of how many times we're in one of the parity or the other parity. And we can see that it can occur 50-50. So now what you see is like the starting point of this experiment, which is a self-organized radiance phase. We're not the first one to observe it. There's also big theory foundations and also experiment has been observed it a long time ago. But here I want to increase more of a lambda. Then what we can see is that we see another critical value, lambda LC, which trigger us to undergo from a super radiance phase into a limit cycle due to Hopf bifurcation. Then how does it look like? So what we did is that we pump the system with the blue detune pump atom detuning. Then we map out this kind of phase diagram. So what we did is like the same experiment, we in time ramping up our pump strength. Then what we changed now is that we changed the pump cavity detuning. So basically the pump frequency. Then we detect what is the number of photons we see in the cavity. Then we stack them up in series as you see that the Y is the frequency of the pump, X is the pump strength. And then we can see that if there's no photons detect, the system is in a normal phase. If we see some photons, the system self-organized into the super radiance phase. But I want to point it out that we also observe a region that has a limit cycle behavior somewhere here. I don't know if it is visible, but at here you would see that there's a bright and dark spot in the series as a pump strength increase. If we stop our pump ramp here and then keep it constant, what we see is that the number of photons oscillate in time with a single frequency, as you see here. If we calculate a Fourier transform of this, you would see exactly one single nice frequency out of this photon number fluctuations, oscillations. And this shows us that we see a type of limit cycle. But in this work, we also go a little bit into the characterization that we call this state a continuous time crystal. And yes, what we did more is that we want to map out a phase diagram where we see a normal phase, superradiant phase, and a limit cycle phase. What we did is that we define a parameter which is called a relative crystalline fraction C. So basically, it's just the height of how high of this frequency in the Fourier transform of your light field. Then we map out this regime. We ramp in, stop, do Fourier transform, calculate C. And then what you can see is that the crystalline fraction is the highest on this edge. So along this edge, for example. Then we use this criteria together with others. For example, if we see no photons, this is in the normal phase. If we see photons, but there's no oscillation, the system is in the super radiance phase. If there's a photons and it oscillates with one single nice frequency, we see the limit cycle phase. And if it oscillates with many frequency that you cannot really well define a single peak anymore, then you see here's the chaotic behavior. And next, what we want to understand is that where is the origin of this limit cycle in our system, as you may know. So what we did is that we construct a minimal model for the system that we have a few modes approximation. For example, here we have 3 modes coupled to one photonic mode. Here the 0, 0 mode is the momentum 0, and the 1 mode here is the superposition of the plus minus 1 h by k. And an additional mode that seems to be important in this case to realize limit cycle theoretically in our system is that we need this 0 plus minus 2 mode along the cavity axis as well. Then we can reduce it up to these 2 bosonic modes plus 1 photonic modes that has a decay rate kappa. What we did again is also a diabatic elimination of the C mode. Then we have this 1 bosonic mode plus 1 mode with self-interaction here, chi. And then you could see that there's one term popping up in the Hamiltonian that it looks like a Kerr-like nonlinearity. And what we did here is that now our system can be reduced up to a few modes with a nonlinear feature in the Hamiltonian. And yeah, you can see more also related works here in the series of them, which construct and find out the origin of limit cycles in different systems. And right, from this view mode, and you see the nonlinearity, then we do the stability analysis by using a fixed point of the superradiant space. What we did is that we have an imaginary part and the real part of the eigenvalues that is related to this. And I want to point it out that if we use the fixed point of the SR phase, then it is clear that all the real part of the eigenvalues has a negative value. Then it is a real steady state. Once it crosses this has a critical value, lambda LC, then this eigenvalue takes up, go across 0. And this shows that the SR is not stable anymore. So then the system forms a kind of limit cycle at this point. And what we see is that one signature of the Hopf bifurcation is that not only the real part crosses 0, but its imaginary partner has to be non-zero at this crossing point. And it's also confirmed that what we see in the limit cycle in the experiment is from the type of a bifurcation of a Hopf bifurcation. So now we have limit cycle forming in the experimental. Then what happened is that if we go on and quench the, pump strength higher, we could also see another type of bifurcation, which is a secondary Hopf bifurcation. So from here, you see one Hopf bifurcation, then what would you expect is that there's a secondary Hopf bifurcation, which is called a Naimak-Zucker bifurcation or a torus bifurcation because its attractors looks like a torus. How does it look like in the experiment? So let's go on. We come back to this phase diagram again. If we stop here of the pump in the limit cycle, we would see this kind of intracavity photon dynamics, which has a single frequency, very nice. Then if we keep at the same pump frequency, but go a little bit at a higher pump strength, what we see is that there's a quasi-periodic of the intracavity photons appear. In the FFT regime, you would see that there's a second peak appearing. And this peak turns out that it is not commensurate to 10 kilohertz of what you see before, but it is at an incommensurate frequency. Then if we continue to do this, we want to map out that there's a regime that limit cycle is not stable anymore, but it is forming another frequency appearing. What we want to do is that we stay at this pump frequency, then we do the same measurement, but then we scan into the different pump strength. And we map it out continuously, you would see this kind of Fourier transform. So in this regime, you would see there's a nice single frequency of the limit cycle. As a pump increased to some range, you would see that there's a second frequency appear at 7 kilohertz. So this shows that in this regime where you see 2 stripes, there's a limit torus appearing. And what we have shown is that there's a dynamic we observe is quasi-periodic because 10 and 7 is not commensurate. And this is the signature of a secondary Hopf bifurcation. And what we can show is also the 3D trajectories. So now this is the updated phase diagram where we rule where is the limit cycle and the limit torus in this regime. And what we can do is that we can also reconstruct a 3D trajectories using Tarkin's theorem. What do I mean is that, so this Tarkin's theorem is telling us that we can construct a 3D attractors by using only one dynamics of the parameters you see. So for example, you have this intracavity photon dynamics at time, so x-axis is time. Then what you do is that you shift this data by a fixed amount of tau. And then you do it by 2 tau, then you see that you have now 3 trajectories in time. And what you did is that you want to plot 3 of them in a 3D plot. And now you could see that this trajectory repeats itself. That looks exactly like a limit cycle where you should have, the trajectories that repeat itself like this. Then what you can do is that you can do the same in this regime where you have a limit torus. And we would expect that it would look like a nesting torus on top of this. So you do the same, you shift it by tau and then 2 tau. Then you plot it on top of this and you get something like this. So I want to point it out that this, I cannot turn this. If you would turn it, you would see that this green line is reducing in the center. This is because of the atom loss, and then you lose the signal in the end. But if this would oscillate for a longer time, you would see that it takes much larger interface space. And this looks, okay, it looks like a torus, I know. But then, okay, this is, a signature that we could see from the experimental data. So now here I come almost to an end, that we have observed a series of Hopf bifurcations in an atom cavity system. Then to complete this route to chaos, let's summarize what is the route to chaos, what we have observed. So before, if we have a pump strength that is below a threshold of the self-organized threshold, you would see just a normal phase. If we look at the intracavity photon, what we detect in time, this is 0. So we see no intracavity photons. Then if we cross this threshold and then the system self-organized, we have a pitchfork bifurcation. That is a bifurcation from fixed point to another fixed point, which is the steady state of a superradiant space. What we see from our observable is that now the photons we observe is still in the steady state, but it is not 0 anymore. So we see a fixed amount of photons. And if you increase the pump strength a little bit across the threshold of a limit cycle, we see a Hopf bifurcation, that the system now becomes a limit cycle where you have a fixed frequency oscillation that just repeats itself. Then if you go on to there, you see a secondary Hopf bifurcation or a torus bifurcation, that you have a 2 frequency in your light fields, which is incommensurate. And then, yes, if you would continue go on, you would see a chaotic behavior as well. So that is where I want to summarize about what is our route to chaos in the atom cavity system. And this work is not done by me alone. I would like to express my gratitude to our team. So I'm from the experimental side, a group led by Professor Andreas Hemmerich. Hans Kessler is our senior postdoc, and Anton Bolien is our master student now. And from a theory side, all the simulations and theory foundations that you're seeing here is done by the group of Professor Ludwig Mattei and Jason Cosmer as well. And Jim Scooter is Ludwig's PhD student. And with this, I would like to thank you for your attentions, and yeah, thanks for having me here.
So it is limit cycle methods. How to identify this bifurcation when you look at the eigenvalues of Scobian or Shifter in order to facilitate the stationary sense? Because normally that's what we do, right?
Right.
real value. It's like you show that we have two things, right?
Yeah.
How is this more people? You explain it?
So I think in the manuscript we also have do this Jacobian matrix analysis that you see that let me see if I have the plot. So there's a signature. If you have a Hopf bifurcation, you would see that your eigenvalues, if you increase the turning knob, which is our pump strength, you would see that the imaginary and real part comes here from the, how to say, so it has to cross this unit circle at non-zero imaginary value, as you can see here. Once it comes here and then cross, then it is shows that you have a secondary Hopf bifurcation or a Niemack-Sacker bifurcation. This I haven't shown. So we use the minimal model and then we use the Floquet analysis. And then you get this type of how to say eigenvalues, and then you plot it in a real and imaginary part. So it will be different behavior if you would have a secondary period double, for example. This would not cross it like this, but it will flop into another how to say, in a negative axis. So this is how we confirm it theoretically, and you see the torus in theory looks much nicer. Experiment, but yeah.
You mentioned from setbacks in context of yeah, this is exactly then going through the
Right.
so Limiters was didn't approach that we use to deduce the equation of motion which is then when you have access to the dynamics. And then the nice thing is that it works for chaotic dynamics you may have, but it doesn't work for stochastic dynamics. It assumes you have the deterministic evolution, which you don't. So I guess I have two questions. One is why exactly are we using the Darkin theory for? Didn't get it. Two, why will you really succeed if you have not shown that you
So the first question is that how do I use Tarkin's theorem for? Because we want to show that this how to say, if we call it a torus bifurcation, we want to see torus attractors as well from the experimental data. And I think Tarkin's theorem is one of the easiest way we can do, because we record one trajectories, then we shift it two times, like you see. Then we plot it in 3D. Then you see a very nice limit cycle or torus. If our data is clean, then we would see exactly like this from the theory. And then what is the second question again? Could you please repeat?
yeah. Nice. Well, maybe what we hope for is perhaps
Yeah.
You're not using it.
No. I think they're not in the sense. I think it's quite powerful what you can use it for, but for us maybe not use it for, how to say, what the at most what it can do. We want just to show that to construct the 3D attractors. So this it can do as well, but not in the sense that what you said. Yeah.
Station says it's good. Building of noise, finest because it's certain sources, silence, sales knowledge. So we just using this idea of representation of so this. Yeah, exactly the aesthetic better way to.
Yes, one last question. Indeed, I lost No.
Du hast men's constitution tries to show you what goes on. And there's also depending on which momentum states you have to use to for your simulation. Now, what happens to your atoms in the limit cycle? This where you can show momentum distributions. I guess they're sad.
So you ask what happened to the atoms in the limit cycles, or
Yes, it can
Cars.
if you want to take now a camouflage.
Right. Yeah.
And it's giving you thing with fluid. Yes, and if you take the simulations.
I mean, in the limit cycle, this is okay. So what happened is that there's a delay dynamics because our kappa is small, right? So, but you can imagine that when you have the peak of your light field, that means you scattered lights very well. So your system self-organized very well as well. So you see a sharp peak, plus minus 1 mode, 0, 0, dash by k. Then when NP drops down, that means you're less self-organized. So you would see a blurry of a plus minus 1 mode. We have a time of flight system, a time of flight data like this, what you see, but not exactly for the limit cycle, but for the driven case where we can trigger the phase of this very well. So you would really see that it's like a very well self-organized, very less self-organized because plus minus 1 mode is dumped, and then you would see a revival of this again. So well organized, less organized, well organized, less organized. So, right.
You hear that?